In this video we're going to make a plot to illustrate Stirling's approximation. Here's what Stirling's approximation says. It says that n factorial is approximately the square root of 2 pi times n to the power n plus a half times e to the minus n. Okay, so that's an approximate formula for factorials. It turns out to be very useful. Some contexts, like in statistical physics for example, where you have to think about n factorial for very large numbers n, and n factorial then is kind of just stupidly enormous, we need to have some kind of idea of roughly how enormous it is, and this formula gives us a good idea about that. We're going to need to import the usual libraries. We're going to need to talk about factorials, and the factorial function is in the math library, so we're going to import math as well. So we're going to make a Python function that returns this approximation here. So we need the square root of np.pi is the thing for get the value of pi, and then we take the square root of that, and then we're going to multiply by n raised to the power n plus a half, and then multiply by exponential of minus n. So let's say Stirling 6, for example, that's 710 and a bit, whereas you should maybe hopefully remember that the real factorial 6 is 720, so that's decent but not terribly precise. Okay, but let's make a plot to see how this goes when n gets bigger. So this is not really working when n is 0, so we're going to start at 1. We've got n's in the range 1 to 21. So range 1 to 21 is, as usual, it stops at 20 rather than 21. And then this Stirling function, I've written it, written a variable as n, sort of indicating n should be an integer, but in fact, this formula here, you can evaluate it, and n is not an integer, so so for the purposes of plotting, it's convenient to consider this Stirling function applied to a variable x that goes from 1 up to 20, and takes kind of fractional values in between. So x's is going to be the equally spaced points from 1 to 20, a decent number of them, and then y is just going to be y's that take this Stirling approximation applied to the x's. Okay, so now we're going to make a plot. So we're going to have so we're going to go. We'll plot it from 0 to 21. So we'll plot it in red as a continuous line. The Stirling function we plot like that. And then we want the real factorial, so there's a math.factorial applied to n. And in this list of numbers n that we've got already. Okay, so here's our two plots. The first thing is, we can't really tell anything too much from this plot because, both of these functions, here we've got 1e18 here, that means 10 to the 18, so everything's going up to about 2.5 times 10 to the 18 as we get to like 20 factorial. and then the early ones are just so much smaller. And so because they're all so much smaller, everything kind of gets squashed down. We can't really see very much what's going on. So the correct way to deal with that is to use a logarithmic scale on the vertical axis. So we'll so I'm going to say we're going to ask for a logarithmic scale on there. So now instead of just going up linearly, it's going up 10 squared, 10 to the 5th, 10 to the 8th, 10 to the 11th. Yeah. Then on the x-axis, we've got we've got these kind of numbers at half integers. That's kind of not really very convenient. Let's change the ticks on the x-axis. Because now we've got these, we don't really have space to have one at every integer. We've just put them in even integers by range 0, 21, 2. It's a 0, starting at 0, stopping just before 21, gaps of 2, so we get numbers from 0 all the way up to 20. Okay, and that's what we've got on the x scale and the y scale there. And then, but now also, so we've got these correct answers here. It'd be better to sort of, for these, there's no real reason to join them up. It's better to make them separate dots. So we put in a little dot there. Okay, so now it does them as dots, and let's make them properly blue. B dot. Okay, so there we've got proper blue dots. Okay, so in the Stirling approximation is the red curve, the correct factorials are the blue dots. And let's just kind of label everything. So the Stirling graph here, let's here, and let's label this. N factorial. Okay, and we run it again. Nothing happens. Where's everything gone? You always need to remember for labels. You need to run the legend thing at the end, just to actually put the labels in the right place. Okay, so there we go. We've got the Stirling function in red, the true factorials in blue, and everything nicely labeled. And that will be it for our discussion of the Stirling function.